Section 6.1, Example 3. On page 427, we have, it is tempting to conclude that the nth root of a to the n equals a for all real numbers a, but part D of problem 2 shows that this is not the case. If n is even, then the nth root of a to the n is positive, even if a itself is negative. For any real number a, the nth root of a to the n is equal to a if n is odd, and the absolute value of a if n is even. It's easy to overlook this rule for simplifying radicals. It is particularly important that you remember it when the radicand contains a variable expression. You must include the absolute value when n is even, and you must omit it when n is odd. So for example 3, we have 3 parts, and we want to know what is a simpler form of each radical expression. For part A, we have the square root of 16x to the 8th. Part B is the cube root of a to the 6th, b to the 9th. And part C is the 4th root of x to the 8th, y to the 12th. The first thing we want to notice in part A is that we're looking at a square root. So we want to see if we can get the radicand to use squares in the expression. We know that 16 is the same as writing 4 squared, and x to the 8th is the same as writing x to the 4th squared. You always multiply the exponents when you've got them right outside the parentheses like this. So now we have 4 squared times x to the 4th squared. Since these are both squared, we can put the 4 and the x to the 4th together. So now we have 4x to the 4th squared, because just like multiplying, we distribute this exponent and it would be 4 squared x to the 4 times 2 is 8. Once we have a square under the square root, because we're looking at square roots and squares which are even, we need to use the absolute value signs like the previous slide tells us. However, 4 is going to always be positive, so we can take the 4 out of the absolute values, and x to the 4th is also always going to be positive because the 4th power is always positive. So the final answer for part A is going to be 4x to the 4th. For part B, we're looking at a cube root, and the previous slide says that if we have an odd power, we do not need to worry about the absolute value bars. Since we're looking at a cube root, we're going to try to get cubes inside the radical. So a to the 6th can be rewritten as a squared cubed, since 2 times 3 is 6. B to the 9th can be rewritten as b cubed cubed, which 3 times 3 gives us the 9. And now we can combine the a squared and the b cubed into one set of parentheses since they are both being cubed. This gives us the cube root of a squared times b cubed all cubed. The previous slide tells us that if we have an odd index, then the answer is just going to be what was inside the parentheses. So we're left with just a squared b cubed. For part C, we have a 4th root, so we want to rewrite the radicand with powers of 4. So x to the 8th can become x squared to the 4th power, y to the 12th can become y cubed to the 4th power. Now we can combine the x squared and the y cubed into one set of parentheses since they are both being raised to the 4th power. This gives us the 4th root of x squared y cubed to the 4th power. Now we have an even index, so we're going to need to include the absolute value signs for what is in the parentheses. This gives us absolute value of x squared times y cubed. However, x squared will always be positive, so we can take that out of the absolute value bars, which gives us x squared times the absolute value of y cubed. Since we don't know if y cubed is going to be positive or negative, we do need to leave it in the absolute value bars. The work for this problem is written out on the next few slides with some extra explanation to remind you of when you do and do not need the absolute value bars. And now I would like you to try number 10. Simplify each radical expression. Use absolute value symbols when needed for the 5th root of 32y to the 10th power.